Good afternoon, Brisbane. How you doing? Good 2 days, huh? So we've had a whole bunch of, really interesting stuff, interesting people, interesting content, all kinds of different topics. We've had people learning about architecture and the web and WebAssembly and edge computing. And I often ask myself, what kind of developer goes to a talk about plain text? Nice to meet you all. This is me, Dylan Beattie. I am, as Michelle so delightfully introduced me there, I'm a Microsoft MVP. I run the .NET user group in London, UK, where I live, and I'm thoroughly enjoying the weather over here right now, because London right now is miserable. And yes, I decided that all those Rockstar programmer jobs on LinkedIn, the world would be a better place if all of us could just become Rockstar programmers, and so I invented a programming language called Rockstar, which you can all go and check out. Now, there are two things that I want to say right at the beginning of this talk. One, there's a lot of stuff in here which the inspiration and a lot of the material came from things that I learned traveling around Russia and Belarus and Ukraine, where I used to do lots of conferences before the pandemic and then before the war. There is when the invasion happened, as people are like, are you still going to do that talk? And I genuinely thought, am I still going to do it? I thought, yes. Everything that's in here is smart people trying to solve problems that allow us to communicate better across linguistic and cultural boundaries. And I think that's a big deal. I think that's important. If any of you does want to kind of show Ukraine some love, some friends of mine are working with this non-governmental organization. Basically, it's Keep Ukraine Connected. They are sending crews in with fiber optic splicing equipment and electronics and network routers to keep all of that infrastructure up and running until as I like to say, the pendulum of history swings back in the direction of justice, which I'm hoping is going to happen any day now. Now, the second thing about this talk is that versions of it have been on YouTube for a little while. And people on YouTube have opinions, and they like typing them in the little boxes. Like, there's no such thing as plain text, and Braden pops up and says, of course there's such a thing as plain text. Plain text is the text plain MIME ASCII type, or more generally, blah, 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 blah. Ending up in a long final destination chain of events that ultimately results in Arnold Schwarzenegger going back in time to kill your parents. Now, I don't know what Braden had been enjoying the afternoon that he sat down to watch a little YouTube. There's also, one of the nice things about having lots of people watch your stuff is they tell you things you would never have found out without it. It's the whole somebody's wrong on the internet. So there are bits and pieces of this which evolve over time as people contribute YouTube comments and stories and those kinds of things. And yes, we are going to talk about plain text for the rest of the day, because it actually turns out there's really no such thing as plain text. When we talk about plain text, what we are normally talking about, like for a long time, plain text meant ASCII. And ASCII is one of those things. Like, who loves ASCII? Who has opinions about ASCII? ASCII's just it's older than all of us. It's been around since before any of us were coding. It's this ubiquitous thing. And it's really weird to actually pull ASCII apart and look at what it was designed to do and how well it does that job. Because ASCII was designed to operate these and these. Mechanical teleprinters, the kind of computers that were prevalent in the United States of America in the 1960s. 1965 is kind of when ASCII got set in stone, and it hasn't really evolved very much since then. And so to understand the design decisions that made ASCII the way it is, you need to understand what a teleprinter was and why it was important. Because if you look at the bottom block of ASCII instruction codes, there's no actual text in the bottom 32 characters. This is all control codes. This is all ways of controlling your mechanical teleprinter. Now, does anyone here still have a teleprinter? That's not how we do things anymore, right? But backwards compatibility means, by and large, we're still stuck with this. Now, there's the null character at the top, which is all the zeros, which is familiar to anyone who's worked with C or C++. And then we've got start of heading, and if you wanted to do a start of heading on your teleprinter, you'd hold the control key and you'd press A. And if you wanted to do a start of text, you'd hold control and you'd press B. And if your teleprinter was just printing stuff that you didn't want to print, and you're like, stop, 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 end of text, you'd press control C. And that one's kind of survived, because we still do that. It's not teleprinting, but we still write infinite loops. I wrote one this morning. It was delightful. Then we have a bunch of interesting kind of characters. There's an ASCII bell character. If you go onto a Windows machine, open a terminal, type echo space, press Control-G, and press Enter, it'll go ta-da.wav, because that's how a Windows computer interprets what used to be ringing a mechanical bell to like, ding, hey, your program has finished running, you can come and look at your mistakes now. And then we get onto the tabs and the line feeds and the vertical tabs. Now, these were all physical, mechanical components of a teleprinter. A tab was a piece of metal that you would lock in place, and then when you press tab, it would go ka-ching until it hit the tab stop. That was a physical thing you could do. And teleprinters were not terribly sophisticated devices. They came with one font. They couldn't do italics without changing the print head. They couldn't do different font sizes, different font faces. But one of the things they could do was they could do a sort of pseudo-bold effect. Because when you printed a line, this little thing that goes running across the page, that's the carriage. And at the end of the line, you have to return the carriage with a carriage return, and then feed the paper to the next line using a line feed. And if you wanted to do a pseudo-bold effect, you could print a line, and then you could carriage return, and then you could print the same line again. And it wouldn't quite line up, so you'd get the pseudo-bold overtype effect, which meant that a carriage return on its own was useful. A line feed on its own, not so much. You always want to go to the start of the line before you advance to the next one. Now, one of the biggest challenges, even if we restrict ourselves to 1960s 7-bit ASCII flavored plain text, the folks in this room probably still can't agree on how you're supposed to end a line of text, right? Because we have the Linux crowd and the Android crowd and the macOS crowd going, new line, and we have the Windows people going, carriage return, new line. Now, it's not that Windows has mechanical carriages. It's that macOS and Android and Linux and most contemporary Unixy operating systems evolved from Unix. And Unix evolved from an older operating system called Multics. And Multics was the first operating system in history that had device drivers. It's the first system where you could put a little piece of code between your computer and your teleprinter that could say, yeah, if they send us a new line, there's a carriage return as well, because we're always going to do that, so you didn't need to put it in your files. Whereas Windows evolved from, Windows, 11, from 10, from 8, from 7, from 98, from 95, all the way back through MS-DOS to CP/M. And that was designed to run on mini computers, which were designed to be really, really cheap. And so they didn't have device drivers, so you had to send the carriage return and the line feed, otherwise your carriage would fall off the end of the thing. The next chunk of ASCII, one of the interesting decisions that the creators of ASCII had to make is how much punctuation are we going to have? Because they had a limited amount of address space. They only had 127 characters. And if any of you has worked in typesetting or type design, there's how many different kinds of minus signs and dashes and space dashes and things. There's about 4 or 5 of these. The ASCII designers went, you get one. That's it. Minus is the same as hyphen, is the same as M dash, is the same as N dash. You'll figure it out. And it's only in the last decade or so, as reading books on digital devices has become popular, we've started seeing a kind of renaissance of typographers' punctuation marks, which weren't included in ASCII. Then there's the decimal digits. Now, one of the things that computers have to do a lot is they turn numbers from numbers that humans can read into numbers that computers can read and back again. And the way you do this with ASCII is you just chop off the big half. And that leaves you with the binary representation of the numeric value of that digit. And that is blisteringly quick, even if all you've got is a 4-bit microprocessor. Then we get to the alphabet. Now, I remember for years thinking, why 65? Why is uppercase A 65 and lowercase a 97? What is important about those numbers? Why did they pick those ones? And the reason they chose them is that they differ by a single bit. So if you are using an 8-bit mini computer and you want to do a case-insensitive search or sort, all you've got to do is ignore that bit, and then upper and lower case come out the same. You can sort your files based on that. Finally, we mop up a little bit more punctuation, braces, tildes, vertical bars, and we get to ASCII delete, 11111111. And this is because you cannot fill the holes in on a paper tape. The only way to erase information on a paper tape is to punch out the rest of the holes. So you write delete characters, and it punches all the holes out, and you can no longer tell what was on the tape before. So the Americans kind of slap themselves on the back, and they're like, hey, good job, everybody. 127 characters, all you're ever going to need. And for certain cultures, they were right. Like in Australia, where they speak English and have dollars and cents, that was really not much of a problem. In Zimbabwe, where I grew up speaking English and using dollars and cents, it was not a problem. For the rest of the world, some of them were like, well, this is almost good enough. A lot of cultures were like, we can't do anything with this. What do you mean you've solved the world's encoding problems? Now, my personal journey with text encoding started in about 1989 when I just moved to the UK from Zimbabwe with my family. And I had done some homework on the computer and I was trying to print it. And my homework included the pound sterling symbol, which did not make the cut because the 1965 Americans didn't think it was important. So when I tried to print my homework, what came out of the printer was this. Now, the computer and the printer could both do pound signs. What they couldn't do was agree on how that should be represented. And what was happening around this time is a whole bunch of different people, companies, organizations, governments, they were looking at ASCII and they went, well, hang on. There's a 7-bit encoding and we've got 8 bits in a byte. Is anyone using this bit? And it turned out nobody kind of laid claim to it and standardized it. And so everybody jumped in and went, yes, we're going to use the top half of 8-bit ASCII to solve all of our problems. Now, there's a thing you'll encounter called a code page. And a code page is a set of rules that says this is what the top half of ASCII means on this computer, in this application, in this document, today, while the stars are in this particular configuration. As soon as you change any of those variables, you can get into all kinds of mischief. Now, one of the most kind of influential code pages, this was code page 437, which was the default code page on the IBM PC. Now, this was interesting to me because they kept this kind of basic 7-bit ASCII, and then they added the accented characters used in Northern and Western Europe. They added box drawing characters so they could do GUI menus and things. They added half of the Greek alphabet. Not the whole Greek alphabet. They didn't have space for the whole Greek alphabet. They added about half of it, because they weren't interested in Greek, they were interested in maths and physics. And they wanted to be able, so kind of all the symbols you'd find in a high school maths or physics textbook are in code page 437. But then someone had the idea of saying, well, the IBM PC isn't a teleprinter, why don't we reuse that bottom block as well, and then we can add little playing cards and smiley faces and those kinds of things. And if you've ever seen an original IBM PC crash really hard, what you get is you get a screen full of little smiley faces and playing cards. Because all of the low-valued machine code instructions that were supposed to be executed end up getting dumped onto standard out instead, interpreted with this code page, and so you get the screen full of laughing, smiling gibberish. Now, there was a whole bunch of efforts around the world to standardize code pages for different alphabets and cultures, and there was an international standard for the Cyrillic alphabet, which is used to write Russian, Ukrainian, Bulgarian, a couple of other Slavic languages. But there was a problem with this. Even though we had 8-bit character encodings, a lot of systems that were prevalent in the 70s and the 80s assumed that text was only ever going to be 7 bits. And so they'd use the 8th bit for parity checking, for spell checking. They just drop it, you know, for doing network stuff. To this day, SMTP email is a 7-bit protocol. And so if you sent someone a message that said, Privyet, hi, hello, in Russian, using the standardized encoding, it would come out as this, and then WordStar would come along and it would chop the 8th bit off all of your words when it did a spell check. And when that came out the other end, you'd get unreadable gibberish that didn't make sense to anyone. So the Russians went, we think we've got a better idea here, and they invented a thing called the Kodobnema Informacja 8-bit, KOI8. And what this did is it didn't use alphabetical order. It didn't use the Cyrillic alphabet. It used the Latin characters, the sort of English language or English alphabet characters that were phonetically similar. So if you took Privyet with KOI8 encoding and you ran it through WordStar or sent an email and you lost your top bit and then you decoded it at the other end, you'd get readable English ASCII that sounded like mangled Russian, so you could still figure out what it was that it actually said, which I think is quite a neat hack. Now, after I did this talk at an event last year, someone came up to me and said, do you know the story of the Harry Potter book? I was like, no, tell me the story of the Harry Potter book. And they pointed me to this lovely little footnote in internet history. Around 2002, there was a woman in France and a woman in Moscow who were pen pals on like a Harry Potter fan site forum. And the new Harry Potter book was available in France, but it hadn't been published in Russia yet. And so we know Svetlana's name because you'll see the evidence in a minute. I don't know who the French lady was, so I've called her Claudette. But Claudette basically said, hey, do you want me to send you the new Harry Potter book? And Svetlana writes back and says, that'd be amazing, we can't get it in Russia yet. Here's my address in the Russian alphabet, please copy it carefully. And then there's a street address of an apartment building in Moscow. And this, send, 2002, probably Windows 2000, Microsoft Outlook, code page encodings. Claudette opens her email and gets this. Now, no information has been lost. Nothing has been mangled here. This is the same sequence of numbers, numeric values, being interpreted using a different code page. But Claudette follows the instructions and very diligently copies out the Russian language street address onto an envelope and posts it. And somebody inside the Russian postal system goes, I know what's going on here. And they decode it by hand. And it ends up getting delivered. Right, a little audience participation, folks. Everyone get your phones out. I want you to open Spotify or Google Play or Apple Music, whatever you use to listen to music on your phone. And I want you to search for this word. You found anything? Billy Joel. Billy Joel live in Leningrad. 1987, Billy Joel and his band become one of the first Western artists to perform live in the Soviet Union. And they played a series of concerts in Leningrad, which is now St. Petersburg, which were recorded, and they were released in the USSR, and the album was called Concert. But on the cover of the album, the word concert is written in Russian. K-O-N-C-E-R-T. And then somebody gets this recording and is like, they need to put it into their database. And the person doing the data entry has an American keyboard, because they work for an American record company. So they're like, K-O-H-U-E-P-T, enter, done. Which doesn't matter, because this is just internal inventory tracking in the 1980s. But once you've made a database, has anyone ever tried to kill a database? You can't kill a database. But, technology progresses and we invent streaming, and someone rings Sony, BMG Music, or whoever it is, and like, do you have a database of all your records? And they're like, yeah, absolutely, and they send it over. And this forms the basis of the catalogs that are used for streaming deals. And so to this day, Kohuept, live in Leningrad, this is just the title of the album now, thanks to a Latin to Cyrillic alphabet encoding problem. Now, there is one more little funny detail about this wonderful intersection of Latin and Cyrillic and music. Does anyone here, any of you folks read Russian? We got any Russian speakers in the room? Do you know what this says? It says nothing. It's gibberish. But if you type this on a Cyrillic keyboard layout, this is the pattern of keys that you press. And if you press that same pattern of keys on a British or an American keyboard layout, but the thing is, Google knows about this, because if you forget to switch from Cyrillic back to American or English when you do a Google search, Google knows what you were looking for, and it knows you forgot to switch layouts, and it will find you the search results for the stuff you want, which I think is actually a really neat hack. Now, this code page system proliferated. It solved a lot of problems, but fundamentally, there was just too many different ones. Like IBM had Bulgarian, but IBM Bulgarian wasn't compatible with PostScript Bulgarian, which wasn't compatible with Apple Bulgarian. And every different language, alphabet, manufacturer, device operating system, we had this vast array of incompatible systems. And as the web and email took off and people actually wanted to talk to each other across linguistic boundaries, we needed a better system. And so the Unicode Consortium was born. And the Unicode, the project started in 1988. The consortium itself was kind of ratified as an entity in 91. And they have this wonderful mission statement to provide a single, consistent way to represent each letter and symbol needed for all human languages across all computers and devices. Now, I break that down into, there are three things here I think are interesting. All computers and devices, if you want to do that, you need to create something which is technically brilliant, completely free, free as in beer, free as in speech, no patents, no licenses, no restrictions, and remove every possible reason why somebody might not be able to use that. And they succeeded. Unicode is why we can send each other text messages with different alphabets and languages. All human languages includes all of the ancient ones, includes ancient Sumerian, includes Egyptian hieroglyphics, because archaeologists, people doing historical research, they want to send email as well. Let's include all of those. So then we get a single consistent way to represent each letter and symbol. And this one is way more complicated than it looks. How many letters are on the slide? Hands up for 2. Hands up for 3. Hands up for 4. Let's ask JavaScript. Let's stop being sneaky. I'm going to put this in a monospaced font now so you can see what's actually going on. What we have here is we have this is a character that is used in Dutch, in the Netherlands and the Dutch-speaking part of Belgium. It's called a digraph. And there is, and was, and still is, some not necessarily dispute, but some good-natured disagreement as to whether this is actually a letter or not. Now, the closest this has ever come to serious hostilities, I think, happened about the game of Scrabble. Now, for a long time, if you bought a Dutch-language Scrabble set in Belgium, in Antwerp, it would include this tile. If you bought a Dutch-language Scrabble set in Amsterdam, it would not. And then you would have the family over for Christmas, and you'd be sitting around, you'd have had a couple of glasses of wine, you'd suggest a game of Scrabble, and Aunt Marie would play ijsvrij, which means ice-free. It's when you get the day off school because the roads are frozen. And she would go, yay, I got a 50-point bonus for using all my letters. And you'd say, no, Aunt Marie, ijsvrij is only a 5-letter word. And of course, no family has ever come to physical violence over Scrabble at Christmas dinner. That never happens, right? And so eventually, to prevent a diplomatic incident, it was decided that as far as Scrabble was concerned, I was not a letter of the alphabet. I and J were going to be separate tiles, and you had to play them separately. So now the Flemish and the Dutch agree on this, but if you travel around the Netherlands, you will still see road signs and all kinds of signage where if a word starts with A and it's capitalized as if it was a single letter. And school kids learning cursive learn to write it as a single letter. So even the Dutch and the Flemish still among themselves aren't quite sure whether this is one letter or two and in what context it should be capitalized and stuff. And we are just getting warmed up. Let's meet some friends of mine. So we have Francois Borde, the archaeologist, he's French, and Motley Crue, the rock band from Los Angeles, United States. And the first time Motley Crue toured in Germany, they did not know why the audience was chanting Mötley Crüe, until someone explained that the heavy metal umlaut is actually a proper letter of the alphabet in Europe, and it's not just there to make you look cool. So Francois the archaeologist went to the Motley Crue concert. Now, this sentence is written in English, right? It's a perfectly good English sentence that just happens to include 4 letters and glyphs that are not part of the regular Latin alphabet. We've got a C with a cedilla, we've got a little AE, typographer's ligature, and then we've got the U and the O, the O and the U, with the diaeresis on top, the heavy metal umlaut. Now, making Motley Crue look stupid, no big deal. They kind of did a pretty good job of that for themselves. But turns out there can be all kinds of really serious social and political implications to what happens when we have to map names between different alphabets. Some of you might have met this guy or know him. This is Magnus Martinsson, he's a Swedish Azure MVP. Except that's not his name. Magnus is Swedish. His name is Mortensson because the A has a little circle over the top of it. Now, this is the 27th letter of the Swedish alphabet, because the Swedish alphabet has 29 letters. And Magnus was traveling to the United States a few years ago to go to an MVP summit at Microsoft on his Swedish passport. Now, if you look at your passport, you've got these 2 lines across the bottom. They have to be ASCII. They have to be 1960s American-flavored ASCII because, I don't know, because mainframes and COBOL are never going away. The Swedish government says that if you have to ASCII-fy the letter O, you use 2 A's, M-A-A-R. Whereas the people who printed Magnus' airline ticket, they just take the circle off the top because they don't know what the circle means. So Magnus is trying to get into the United States with an airline ticket that doesn't exactly match the name on his passport. Good game. Now, he just explained a little bit about this, and but he's an articulate, well-dressed white guy on his way to a software developer conference at Microsoft. The American kind of border authorities, in fact, border authorities all over the world, you can imagine how for all kinds of people, a transliteration error between the alphabet that their name was normally written in and the ASCII on their passport could lead to all kinds of headaches. And we are only just getting warmed up. We're going to take a list of European cities: Berlin, Aachen, Zurich, Aarhus, and Örebro, and we're going to put them in alphabetical order. Which one do you think is in alphabetical order? Hands up for number 1. I mean, it's obvious it's A, A, B, O, Z, right? That's alphabetical order. Hands up for number 2. number 3, number 4. Impressive. They all are. Every one of these lists is in alphabetical order for a particular alphabet. We're going to put them in a SQL Server database because that's what I do for fun. And I'm going to go in here and I'm going to say, all right, let's select star from cities. There we go. We got our data. Now let's select star from cities where name equals Orebro. And it's like, nope. I'm like, hang on. I'm sure we put that in. Maybe it's case sensitive. Let's put a big O on Orebro. Nope. If Orebro equals Örebro, print yes. Otherwise, print no. No, it doesn't. We need to learn about collations. A collation is a set of rules for just saying this is what alphabetical order means. These letters are equal, and if they're not equal, which one comes first? The Latin general case-insensitive, accent-insensitive collation, CI-AI, is, I think, the most sensible default for configuring databases in the modern world, because most of the time you'll probably find what you were looking for, even if you don't have that exact key on your keyboard. And according to that collation, Örebro with the diaresis and Orebro, they are the same, so you can find what you're looking for. Now, we're going to select star from cities order by name. We're going to do the same thing with that Latin collation. We get what makes sense to me as a native English speaker, A-A-B-O-Z. To me, that looks like alphabetical order. Now we're going to do it using Finnish and Swedish collation. And at this point, that 29 letters of the alphabet rule kicks in, and it goes, well, yeah, is the 29th letter of the alphabet. So A-A-B-Z, and then is after Z, because 29 is after 26. Now we're going to use the Danish and Norwegian collation. Now, we need to learn a little bit of history here. We're going to talk about Aarhus. Now, Aarhus is Denmark's second city after the capital, Copenhagen. And the city of Aarhus was officially spelled Aarhus from 1948 until the 1st of January 2011. In 1948, there was a thing called the Danish Spelling Reform. In the aftermath of World War II, the people and government of Denmark decided that they wanted to be culturally closer to Sweden and further from Germany. You can probably figure out why. And so they extended their alphabet. They didn't use the exact same letters, but they used some sort of subtly different letters. They extended the Danish alphabet from 26 letters to 29. And they made a rule that said places, companies, people in Denmark that were spelled with this or sound, if they wanted to, they could change to be spelt with this new letter of the alphabet. So Aarhus, AA, became Aarhus with the or on the beginning. Then in 2011, the mayor of Aarhus decided to change it back because it was interfering with Google PageRank. But that doesn't change its position in the alphabet. It just changes the way it looks on the page. The list on the right here is in completely valid alphabetical order in Denmark and Norway. Aachen goes at the beginning because it's in Germany, and so it's pronounced A. But Aarhus goes at the end because it's in Scandinavia and it's pronounced or. This makes perfect sense to people who grew up with it and no sense whatsoever to anybody else on the planet, because that's the thing about culture. The thing you grew up with obviously makes sense, and everything else is other people being weird. Now, if you actually have a scenario, the problem here is there's not enough data in the database to get that right for the Norwegian and Danish cultures. The only way to do that consistently, if you actually have to do this as a requirement, is you got to put another column in your database, which you're going to use as a sort key. And if you need to support multiple cultures which have these unusual orthographies, you're going to have a sort column for each culture you support so that you can get things to come out in the right order. And now we can coalesce by that sort name, and we get Aachen at the beginning and we get Aarhus at the end, which is what makes sense for those markets. Now, people often say, I like working with technology, I'm not interested. Leave the politics out of it. If you want to know why a file called aardvark appears at the end of the listing on Danish language windows, you need to understand World War II and the Danish spelling reform and orthography and all these things that happened. There is no technology which is politically agnostic, because politics creates the problems and technology tries to solve them. If there was no politics, we wouldn't be here. We'd be out on the beach having fun or something. Now, we can at least agree that if we have a lowercase letter and an uppercase letter, maybe you have them in your alphabet, maybe you don't. But at least the mapping between the two is always going to be consistent, right? Like this is at least something we can agree on? Nope. Earlier this year, I was supposed to travel to Istanbul. The trip got rescheduled, but I had booked an airline ticket and everything. I went into my Google Calendar and I noticed that I had a flight to Istanbul. And Istanbul has a capital I with a dot on top of it. Because in Turkish, there is a dotted and a dotless I. And the dotted I has a dot, whether it's upper or lowercase, and the dotless I doesn't have a dot, whether it's upper or lowercase. But it isn't a special letter of the alphabet. The decision that was made by the Turkish Language Committee in about 1934 was that the lowercase letters, they're just going to use the English one. But when you uppercase it, it becomes the Turkish special one, and vice versa. So when you capitalize internationalization using a Turkish culture locale, you get internationalization with dots on the I's, and when you lowercase this one. Now, the yellow characters are special. Everything else on this slide is still regular ASCII. So if you are turning ASCII into uppercase in Turkish, it's going to teleport some of the letters into the middle of a Unicode block. As Wikipedia very diplomatically puts it, has caused some issues in computing. But this is one of those wonderful things, like people are like, that doesn't make any sense. I'm like, you come up with a better system, and people kind of scratch their head and they're like, what about it? And it's like, no, if you do that, you end up with two keys on your keyboard that have the same letter on them, and they're like, oh yeah, that's not going to work. We could do this. Like, no, we're not suggesting that Turkey delete an entire letter from their alphabet and mash the remaining pieces together just so they work with American computers. They're like, yeah, that would also be about it. There's no elegant solution to it. Any way you slice it, it produces these problems. Let's talk about this. Now, the C with a Sadira on it. One of the things, kind of the guiding principles of Unicode is that it never set out to tell anybody how to do their jobs. What it did was try to create a set of tools that allowed us as developers and engineers to choose the approach that works best for our solution. And so if you have to write C in Unicode with the Sadira on it, there is a single code point you can use, this character, 00C7, or we can take an ASCII-flavored C and we can put a tail on it using what's called a combining character. Now, the lovely thing about combining characters is that you can stack them up. And you can say, put one of those, one of those, one of those, like ordering a cheeseburger with all of the extra toppings, just stack them all up until you get Zalgo text. And this is a great way of testing the text rendering engines. Like if you're building a piece of software that's rendering TrueType fonts, throw some Zalgo text in it, it'll fall over, and it will fall over somewhere you didn't think it was going to fall over. But then this gives us another set of problems. Let's take our friends in Mötley Crüe again. And we could write the word Motley Crue as M, O with a diaresis, T-L-E-Y, or we could write it like this using combining characters. Now, when you render these two strings on almost every device, they look the same, they sound the same, they mean the same thing, they are semantically equivalent, but it's not the same set of bits. It's not the same sequence of digits. So Unicode says, well, again, we're not going to tell you what's right or wrong, we're going to give you tools to fix it. We're going to give you normalization forms. Now, there are four of these. There's what's called the canonical decomposition and canonical composition. Decomposition means you break a string out into the widest possible number of code points. Composition is the opposite. You crunch it all together. And then the other form is called compatible, except we've already used C to stand for canonical, so that's not going to work. So Unicode spells compatible with a K. So the NFKD is the compatible decomposition normalization, and there is also a compatible composition. Now, what these actually look like in practice, every language that I've come across has normalization support built into it somewhere. And I just threw together a little snippet. This is in C#. I've got examples in Java and JavaScript if anyone wants to see them at the end. And what I'm going to do is I'm going to build the string Motley Crue in two different ways. One of them I'm going to build just by sticking characters together. The other one I'm explicitly going to put in this Unicode combining diaresis code point. And then when I run the example on that, it's going to say, all right, they're both length 11. Now that's interesting. String length gets very complicated when you get into these kinds of things. But it's like, no, a human being would count, like if you press backspace 11 times, you've deleted the whole string, so it's 11 characters long, which is about as good a definition as you're going to find. Are they equivalent? No. S1 equals S2 is false. These are not binary equivalent, but all four normalization forms say this is the same thing. Now we take another example here. We got the string plain text, but when we got the string plain text in like funky Unicode bubble writing, which is a thing that apparently we needed. And if we run the same string comparison on this, what we get with this example is, again, they're the same length, they're not equal, and they are not equal under the canonical compositions, but the compatible ones, it goes, well, yeah, they both say plain text. So if you are building some kind of system where people can put in social media usernames and they're putting in funky little Unicode italics or bold characters or mathematical characters, but you kind of still want to be able to search for their username, you need to use the compatible composition forms. Now, The second installment in my life's great journey with text encoding came about probably sort of 7, 8 years ago. I got into work one morning and one of my team said, dude, I think we've been hacked. Now, this happens all the time in tech because humans click things they're not supposed to click on and then they come running to you about it. But when somebody who is actually a very competent security engineer says, I think we've been hacked, you're like, why do you think we've been hacked? There's Chinese in the Windows event logs. Now, we're a British company based in the UK. To the best of my knowledge, none of our team spoke, read, or wrote Chinese. We had a handful of Chinese customers, but we didn't do business in China. We didn't localize any of our software into Chinese. But sure enough, there was Chinese in the Windows event logs. So Incident Management 101, right, I need you to go to the business, tell them we've got this weird thing going on, we might have had a data breach, we've got an update for them in 15 minutes. I need you to go check the firewalls, see if there's any interesting traffic, look for Chinese IP addresses. You go and search all the tables, is there Chinese content? Is this some kind of SQL injection attack? You delegate all the important bits you can think of, because then you get to sit back and shitpost about it on Twitter. Which is often a winning strategy, or at least it was before Elon Musk bought Twitter and spoiled it for everybody. I posted this, and 18th October 2016, there, you can see exactly where it was, and I got a reply from a friend of mine saying that looks like a Unicode mapping error. And then the fake Unicode account popped up and said the low bits are all null, so this is UTF-16LE being mistaken for UTF-16BE. And I look at this and I think, it might be a really good time for me to learn what any of this stuff means. So I dive headfirst down the rabbit hole of big endian and little endian encoding, and this is what I learned. There's a thing called UTF-16. Internally, so Microsoft Windows, Java, JavaScript, .NET, they use 2 bytes for most text. So when you have a string in memory in your database or your operating system, it's almost certainly stored as 2 bytes. So anything that is stored as ASCII, one of those bytes is always going to be null because you only need the other one. But the 16-bit width, that means your string lengths are predictable. It means memory allocation. If you know how big a string is, you know how much memory you need to allocate to be able to read that string from disk, these kinds of things. Now, big endian, little endian is what happens when these bits get flipped around. And if you take the word delete, perfectly normal database operation, and flip it around, you get this. Anyone here read Chinese? Somebody on YouTube does, because they commented, yeah, that one means dismembering the body of livestock. That one means climbing. That's a category of textile fabrics. And now, when I saw this comment, it reminded me the day this happened, somebody ran the Chinese from the event log through Google Translate, and then came over and said, I think this might be like a ransom note. I'm like, why? And I was like, it's very mangled, but I think they want us to cut up a chicken and put gemstones in it. I'm like, I don't think it's a ransom note. Anyway, so we eventually figured out what had happened. This took like 27 hours, because what was happening is the Chinese was happening for 3 minutes. And then it was going away for about 3 minutes. And then it was coming back again. And so every 3 minutes we'd be like, it stopped. Have we fixed it? And of course, we've got the team trying various rebooting things and checking things. And it keeps thinking, did that fix it? No, it came back again. What we eventually worked out, it wasn't that the bits were getting flipped. It was that there was a faulty network switch in the data center that was hosting this application. And so the network connection between the CRM server and the SQL database server, every 3 minutes it was just dropping a byte silently. Just one byte wouldn't make it out the other end of the pipe, which meant everything else got shunted sideways. And the thing on the other end went, well, obviously it's Chinese time over here again. And then 3 minutes later, it would drop another one. It would all shunt across again. Now, UTF-16, like I said, it works brilliantly for operating systems and programming languages where speed is a priority. You want things to be fast, you want things to be predictable. Once you get out onto the network, and particularly onto the web, the parameters kind of tip in a different direction, because even if you're writing web pages in Ukrainian Cyrillic, HTML is based on ASCII, CSS is based on ASCII, JavaScript is based on ASCII unless you're really, really evil. And so if you take a web page like this one and you encode it using UTF-16, the bits in blue are the bits where the Unicode is important, because that's Ukrainian Cyrillic. That's not part of ASCII. The rest of it, we are sending null, ASCII, null, ASCII, null, ASCII. And we have to send the whole thing. We can't just ignore it and say, look, just put nulls in where you think they need to go, because that's not a thing that works, which means 44% of this payload is redundancy. It's just us saying null, 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 null over and over again. And this is where Unicode comes in with what I think is the most beautifully elegant hack, possibly in the whole sphere of computer science. It's a variable width encoding called UTF-8. And what this says is you got a bunch of bytes on a data stream. Any byte starting with a 0 is 7-bit ASCII, same as it's been since 1965. That stuff is all backwards compatible. If you have a byte that starts with a 1, that is part of a multi-byte sequence. Now, if your byte starts 1, 0, you are in the middle of a letter, you need to backtrack. You need to rewind until you get to a 1, 1, and then if it's a 1, 1, 0, that's the start of a 2-byte sequence. If it's a 1, 1, 1, 0, that's the start of a 3-byte sequence. 1, 1, 1, 1, 0 is the start of a 4-byte sequence. Now, this means that ASCII documents are small. It means that most documents end up about the same as they would be with UTF-16, but it also gives us a huge amount of headroom. So we can keep inventing new alphabets and new glyphs and new languages, and we are still inventing new alphabets because we've invented emoji. And we add new emoji every year. Now, emoji came out of a project around the turn of the millennium. A Japanese mobile phone company, Docomo, had a project called iMode, which was traffic times and public transport timetables and restaurant reservations on sort of 1990s feature phones. And they created this set of emoji to launch with that product. This is in the Museum of Modern Art in New York now. Within a couple of years, you couldn't sell a phone in Japan that didn't have emoji because everyone loved them, which meant when Apple launched iPhone in Japan in 2008, it had to have emoji support. And so the rest of the world worked out that if you set your keyboard language to Japanese, you could type all of these little interesting cartoon characters, and suddenly people started asking questions. Like, there's sushi here, but there's no tacos. How do I tell someone I want to go for tacos? There's a firefighter, there's a pilot, there's a bus driver, they're all men. Why are all the professional occupations in this thing men? Questions about, family composition and gender identity and skin tone, and just people going, look, I want to tell stories about me and my people, and I can't do them because there aren't enough options in the keyboard here. Now, emoji started out as a kind of, an informal handset standard. Then Apple and Google got together and petitioned Unicode and said, this thing really needs to be like a part of the Unicode spec so that we all know what we're trying to support here. So Unicode kind of adopted it and took over. Then in 2015, they made what I think was a really big step towards more inclusive emoji. And they did it in a way I think is really clever. They added the ability to use skin tone modifiers as combining characters. So you could have like a thumbs up, but then just like putting a tail on the ASCII letter C, you could have a thumbs up plus a medium dark skin tone, and then that would give you dark skin tone thumbs up, if your handset supports it. If it didn't, you'd get a thumbs up and then you get a little missing glyph, and then next time you install a phone update with new emoji in it, suddenly you'd unlock all of these new glyphs. Now, there's a whole bunch of variations on these. The emoji for a lady astronaut is the emoji for a woman, a thing called a zero-width joiner, and rocket ship. And the woman and the rocket ship, they both existed previously, so all they did is say, look, if your handset supports it, and we put a zwidge, a zero-width joiner between them, combine them and display a single piece of artwork. If they don't, you get a woman plus a rocket. You update your iPhone, suddenly you have Lady Astronaut. And you can do a female astronaut with dark skin tone modifier plus the zwidge plus the rocket ship. And so you have all these different combinations of people and professions and things, all done using technology which was created in the 90s before anyone had ever thought of doing emoji at all. Now, flags, I think, are really interesting. The flag of Australia in Unicode is the regional symbol indicator letter A and the regional indicator symbol letter U. All the countries that are recognized by the United Nations and ISO have a flag using their 2-digit country code. England is not a country, according to ISO. Great Britain is, or the United Kingdom of Great Britain is, but England is only a country when it comes to rugby and football and stuff. It's not a proper country. But people care about rugby and football. They want to be able to fly the flag. And so Unicode says, all right, well, you can have the black flag plus the tag letters GBENG, which is the same strategy that's used for the flag of Scotland, the flag of Wales, and the flag of Texas are in there as well. These are the other geographic flags that are supported. And then the pride flag is a white flag, a zero-width joiner, and a rainbow. Now, anyone recognize this flag? Anyone know the official name of the country that this flag belongs to? The Republic of China. not to be confused with the People's Republic of China. The Republic of China is the country most people know as Taiwan, and it is a little bit politically sensitive in certain parts of the world. So if you go onto your iPhone and you type in Taiwan, you get the keyboard, and you can put the key in, you can draw the flag, but then you go into your settings and you change your phone's region to China mainland, and when you go back and refresh it, the flag has disappeared. Because the Taiwanese flag on mainland China, the People's Republic of China, is seen as a symbol of Taiwanese independence, and they don't like that. They do not like support for that. Apple wants to be able to sell iPhones to the billion or so people in China who have money. Chinese government doesn't want any Taiwanese flags. Apple says, all right, we'll take it off. And they've just done like a weird thing, like when Hong Kong became part of China again. In Hong Kong, you can see the flag, but you can't type it. So you're allowed to look at it, but you're not allowed to, it's missing from the keyboard, which I just think is bizarre. Now, this is the kind of thing that device manufacturers have to take into account when they're thinking about, pushing and launching devices in all these different markets with their different political alignments and sensitivities and things. Now, if you go onto my Twitter profile, I've got a little Aussie flag on there at the moment because I'm at YOW Brisbane. And if I go to edit my Twitter profile on macOS, I get the Aussie flag in the text box. And if I do the same thing on Windows, I don't. I get AU, and I can't type the flags. Microsoft Windows does not include any geographic flags. That's their solution to the whole China, Taiwan, and that category of problems, is we are not touching that. No, you are on your own. There are 3 flags that are supported in the Microsoft Windows operating system. They are the pride flag, the pirate skull and crossbones, and the checkered flag that denotes a Formula 1 race. Which to me means Microsoft's official position on emoji flags is gay pirates are winning, and everyone else can get in the bin. Now, I want to leave you today with something useful, something you can take away and you can use for enlightenment across the rest of your career. First time I visited Ukraine in 2016, absolutely amazing country. I was there doing a couple of conferences. I had a blast. I couldn't read anything. I could not read the Cyrillic alphabet. I'm wandering around the place. I have no idea what the beer I'm drinking is called or the bar I'm drinking it in is called, but I can read the license plates on the cars. And I said to one of the folks out there who we were out with one evening, I was like, why did they use the English alphabet on Ukrainian license plates? And he gave me this look like, what? We don't do that. I'm like, look, we can read them. So I went down the rabbit hole. I was like, how did we end up with this situation? I discovered a thing called the 1965, the same year as ASCII, there's a thing called the Vienna Convention on Road Traffic, which was a treaty that a whole bunch of countries in Europe signed about if we want to drive our cars across the borders into each other's countries, it'd be a good idea if we can read and write each other's license plates. The Soviet Union was a signatory to the Vienna Convention on Road Traffic. Now, in 1965, one of the stipulations of this treaty, by the way, is that the license plates had to be written in the Latin alphabet, the English Latin alphabet. In 1965, Soviet license plates looked like this. Now, I'm guessing there was a meeting where somebody said, comrade, why are we signing the treaty if our cars don't have Latin license plates? And someone said, comrade, you do not drive car out of Soviet Union. Because, travel was heavily restricted. And if you could get a permit to drive out of the USSR, they would give you temporary license plates at the border, and you would bring them back. Oh, yeah, you would. But then in the 90s, when the USSR dissolved into, the independent states, all of these countries reformed their traffic registration systems. And so now if you go to Ukraine, Belarus, Russia, even if you can't read Cyrillic, you can read every character on the license plates. And the way they did it, I think, is clever. The Ukrainian Cyrillic alphabet, so the system they use in Ukraine, takes the set of glyphs, the intersection between the Latin and the Ukrainian alphabets. Now, this is not the set of letters, because they don't read the same sound, but they are the same shape. Uses that set of shapes, and that is the set of characters they used on their vehicle registration systems. And if you take that set of letters and rearrange them in English, it spells PIKEMATCHBOX. Now, I want you to remember that, because next time somebody says, I'm going to send you a plain text file, you can say to them, do you know about PIKEMATCHBOX? And if they say, yeah, I know PIKEMATCHBOX, then they know about big endian, little endian code pages, the Danish spelling reform, Norwegian collation, license plates, all that kind of stuff. And they're probably going to send you a file that behaves the way you expect it to and will open in your favorite editor. And if they say no, what's PIKEMATCHBOX? Then they're going to send you a file that works on their machine. And what happens when you get it is anybody's guess. And I'd like to dedicate this talk to a guy called John Doe, who watched the whole thing on YouTube, all 1 hour and 5 minutes of that version, and then commented, "Please leave politics out of software. Thank you." Thank you, folks.